and thank you for taking a look at my poster. My name is William Thompson. I'm a PhD student at the University of Victoria in Canada, and this work was done at the National Research Council, Hertzberg Astronomy and Astrophysics. I'm going to talk today about how we are using Julia as the brain of our control system, reading from sensors and controlling physical hardware in real time. I'm going to briefly step through the panels of my poster. If there's anything I don't cover, I'd love to discuss it with you in the main session. You may have heard before of exoplanets. These are like the solar system planets you are already familiar with, except they orbit other stars. In some cases, like the figure on the right, it's actually possible to take a picture of these exoplanets. Here you see 3 giant planets that are still glowing hot from their formation about 30 million years ago. To make this work for smaller planets, more similar to our own, we need to measure and compensate for the shimmering effects of the Earth's atmosphere and imperfections in our optics in real time. This slide shows a before and after. By controlling the positions of hundreds of actuators, something called a deformable mirror, we can clear up the intense glare from the star. This hopefully reveals an image of any planets that might be orbiting it. Normally, we would need to test out our algorithms in something like MATLAB, but slowed down by about a factor of 100 times. Then this code would be handed over to another team to port to C++ and run on a real-time computer. By switching to Julia for this project, we can do our prototyping at real-time speeds and also avoid a full rewrite when we take our instrument to the telescope. To make this work for us, we developed a modular control system for running our lab equipment and for connecting our control loops. This framework handles linking, scheduling, and synchronizing all of the loops, as well as providing a GPU-accelerated management GUI. Hot reloading is also supported by Revise, which lets you experiment with changes to your control algorithms on the fly without even closing the interface. There's a very basic structure you can fill out for each process. Just specify a setup step and return a closure that performs one iteration of your control loop. Then you list each device and loop you want to run in a TOML file like the one on the right. The rich GUI is thanks to CIM-GUI and implot. Each component gets to draw its own panel for us to control the system. And this video shows it all working together live to control the deformable mirror. Now, Julia is all about speed, but it's more oriented around throughput than latency. A few considerations when using it to control hardware are first that the language is garbage collected. We can write our main control loops to not allocate, but inevitably an allocation will occur somewhere. And eventually this will trigger a GC pause. And second, there are some challenges when receiving data from certain hardware, particularly around receiving callbacks on a foreign thread. That said, we've been able to get our system to work reasonably well. Without optimizing latency too much, we've been able to hit roughly 3 millisecond average time, and worst case, about 100 milliseconds, which isn't too bad. All right, thank you very much for taking a look at my poster. If you have any questions, please ask me during the discussion session. Thank you.